This video is about centripetal acceleration and centripetal force. We'll begin by discussing centripetal acceleration, then we'll move on to centripetal force, and we'll finish up by looking at some real-life examples of circular motion. Let's begin with centripetal acceleration. We'll look at an object that is moving in a circle at constant speed. Motion in a circle at constant speed is also called uniform circular motion. The path of the object is a circle, and we'll assume that the object moves from this point to this point in a certain amount of time. The velocity of the object at any given point is tangential to the circle and looks like this. Let's denote the velocity by lowercase v. Recall that acceleration means change in velocity, and that velocity is a vector, so it has a magnitude and a direction. As you can see from our diagram, when an object is moving in a circle at constant speed, the direction of its velocity is changing, which means that the object is accelerating. At first sight, this acceleration might not be obvious, because we usually think about acceleration as a change in speed. So keep in mind that acceleration is a change in velocity, so a change in the direction of the velocity results in acceleration. Similarly to velocity, acceleration is also a vector. This means that the acceleration has a direction. This direction is always towards the center of the circle, so the acceleration vector looks like this. Let's denote the acceleration with lowercase a. Of course, there is a reason why the acceleration vector is pointing towards the center, and this can be shown by using vector operations. We simply have to subtract the initial velocity from the final velocity. Since this proof is not an essential part of the IB physics course, I will not show it here in detail. The centripetal acceleration also has a magnitude. There are two formulae in the IB physics data booklet that can be used to calculate the acceleration. Here are the formulae. And here are the variables that are present in these formulae. Just like the direction of the acceleration, the formula for its magnitude can also be deduced by using mathematics. Again, I won't go into the details of this deduction here, because it is not part of the IB physics course. Just be aware that there is a reason why the formulae look like this. We also learned earlier in topic 2 that acceleration happens when the resultant force or net force on an object is not equal to 0. The force responsible for centripetal acceleration is called the centripetal force. Let's explore this centripetal force in more detail. To examine the centripetal force, we'll go back to our object that is moving in a circle at constant speed. We saw that the direction of the centripetal acceleration is towards the center of the circle. Logically, the centripetal force is pointing in the same direction as the centripetal acceleration, so also towards the center of the circle. We usually label the centripetal force as FCP. As we said, the direction of this force is towards the center of the circle. To find the magnitude of the centripetal force, recall from topic 2 that force is equal to mass times acceleration. So FCP is equal to m times a, where m is the mass and a is the centripetal acceleration. We saw that the centripetal acceleration is equal to v squared over r, so we can simply substitute this into the equation. This gives us that FCP is equal to m times v squared over r. This is one of the two formulae to calculate the centripetal force. In the previous video, we learned that v, the linear speed, is equal to omega times r, where omega is the angular speed and r is the radius. Substituting this in place of v, we get that FCP is equal to m times omega r to the power of 2 divided by r. Expanding and simplifying by r gives us that FCP is equal to m times omega squared multiplied by r. This is the other formula for calculating the centripetal force. Both formulae can be found in the IB Physics data booklet, and they look like this. Here are the variables in these formulae. There are many real-life situations when objects move in a circle. Let's examine some of these situations in more detail. One way to explain centripetal force is that it is the force necessary to keep an object moving on a circular path. A key point here is that the centripetal force is not a type of force. Let me explain this a bit better. By type of force I mean, for instance, gravitational force, electrical force, or magnetic force. When an object is moving in a circle, we can say that the centripetal force is a result of a certain type of force. We'll see 6 examples to make this more clear. A satellite orbiting a planet, a car turning a corner, a stone that is attached to a string and is made to move in a horizontal circle, a bicycle that is banking, an electron that is orbiting a helium nucleus, and finally a proton that is moving in a magnetic field. All these situations involve circular motion, so let's see what type of force is causing the circular motion in each case. When a satellite is orbiting a planet, it is usually moving in a circle. The center of the circle is the center of the planet. The force that keeps the satellite on this circular path is the gravitational force that the planet exerts on the satellite. So we say that the force providing the centripetal force is the gravitational force that the planet exerts on the satellite. In the second example, a car is turning a corner. The car is able to follow a circular path because of the friction between the tires and the road. Without friction, the car would just continue sliding straight instead of turning. Unfortunately, this happens sometimes, especially on icy roads where friction is low. So here, the force providing the centripetal force is the friction force between the car's tires and the road. In example 3, a stone is attached to a string and is made to move around in a horizontal circle. The stone is able to move on a circular path because the string is continually pulling it towards the center of the circle. A more formal way to say this is that the force providing the centripetal force is the tension in the string. In the next example, a bicycle is banking. Banking here means that the cyclist is turning a corner and at the same time he's leaning sideways towards the center of the circular path. Let's assume that the biker here is banking because he is traveling around a sloped curve. The curve is sloping in towards the center of the circular path. If we are looking at the biker from the back, the situation looks like this. There are 2 or possibly 3 forces acting on the biker. The gravitational force vertically downwards and the normal reaction force. When only these 2 forces act on the biker and there is no friction force, the vertical component of the normal reaction force is equal to the gravitational force, while the horizontal component of the normal reaction force is pointing towards the center of the circular path and provides the centripetal force. If we take into account friction between the tires and the ground, we can draw the friction force like this. The friction force is parallel to the slope. In this case, the centripetal force has 2 components. One of them is still the horizontal component of the normal reaction force, while the other component is the horizontal component of the friction force. Summarizing this, we can say that the force providing the centripetal force is the horizontal component of the normal reaction force, and in some cases also the horizontal component of the friction force. In example 5, an electron is orbiting a helium nucleus. We'll learn more about electron orbits later in topics 7 and 12. For now, let's just assume that an electron orbits a nucleus, just as a satellite orbits a planet. So what force is providing the centripetal force here? The electron is negatively charged, while the helium nucleus is positively charged. This means that there is an attractive electric force between the electron and the nucleus. It is this electric force that keeps the electron in orbit. Therefore, the force providing the centripetal force here is the attractive electric force between the electron and the nucleus. In the final example, a proton is moving in a magnetic field. Let's assume that the proton is just entering the field. The situation looks like this. Using Fleming's left-hand rule, which we discussed in an earlier video in subtopic 5.4, we can work out that the direction of the magnetic force on the proton is pointing to the right. Assuming that the proton keeps moving at constant speed, it will follow a circular path that looks like this. The exact radius of the path depends on the magnitude of the magnetic force. So in this example, the force providing the centripetal force is the magnetic force that acts on the proton as it enters the field. Let's summarize what we have learned in this video. We began by discussing centripetal acceleration, and recalled from topic 2 that acceleration happens when velocity changes, and that velocity is a vector, so it has a magnitude and a direction. Then we saw that when an object is moving in a circle at constant speed, the direction of its velocity is changing, so the object is accelerating. The direction of this acceleration, called the centripetal acceleration, is towards the center of the circle, and its magnitude can be calculated by using one of the following two formulae. Here are the variables that are present in these formulae. Next, we moved on to centripetal force and learned that logically, the centripetal force is also pointing towards the center of the circle. Then we learned that the magnitude of the centripetal force can be calculated by using one of two formulae, and we added the variables that are present in these formulae. Finally, we saw 6 real-life examples of circular motion and concluded that in different situations, different forces provide the centripetal force. Examples of such forces are the gravitational force, the friction force, the tension, the normal reaction force, the electric force, or the magnetic force. This completes our discussion of centripetal acceleration and centripetal force. In the next video, we'll explore motion in a vertical circle.